This next section is on properties of functions, and we're going to look at several different properties, including functions that are even and odd, and then we're going to look at increasing, decreasing, and constant functions, and local min, local max. Those are some of the things we're going to talk about, and then average rate of change. So look at the top of your notes. It says determine even and odd functions from a graph. So we're going to first decide just by looking and analyzing the graph. So the first graph that you see, again, I am just sketching, okay, looks something like this. Not too bad, huh? Not too good, but not too bad. And it says even functions are symmetric with respect to the y-axis. So even functions have symmetry to the y-axis. Now, what does that really mean? All right, well, here's my x-axis, here's my y-axis. It means that there's some point on my graph that I'm going to call the point xy, and that if I reflected that point across that y-axis, that I also have the point over here, negative xy, so that it is symmetric across the y-axis. Now, the way I drew mine, it actually isn't, because there's not as much space on the left as there is on the right, but you got to look at your own and label those points. One of them is xy, and the other one is negative xy. So we call that an even function. So underneath it, it says that when a function is even, f of negative x, so there's the negative x, is the same as f of x. Now, what does that really mean? It means that if you look at the y for negative x, it's the same as the y for x. Okay, the y's are the same. It's the same distance up off the x-axis. So the y's for x and negative x are the same. So we know that if the point xy is on the graph and the point negative xy is on the graph, then that graph represents an even function. Okay? Let's look at the next definition. The next definition is a definition of an odd function. And I know what you're thinking. Oh, well, if it's even with symmetry to the y-axis, then odd must be symmetry to the x-axis, but that isn't true. Odd functions are symmetric to the origin, and that's an easy thing to remember because of the O in odd and the O in origin. So let me sketch a real quick little graph of that. And that graph looks something like this. And what that means is if I have some point xy, that the other point that I actually have is the point negative x, negative y. If both of those points are on the graph, then it has symmetry with regard to the origin. And you can look at this line, the line x equals y right here, and you can see that those 2 points, if I had drawn it correctly, are symmetric to that origin, the line going through that origin. So that is considered an odd function when it has symmetry to the origin. And what it means is if xy is on the graph, then so is the point negative x, negative y. So what we have underneath it, it says f of negative x is equal to negative y, which means negative f of x. So think about that for a minute. The negative x gives us a negative y, or a negative f of x. All right, that's an odd function. So let's look at example 1. I think you'll feel a little bit better about these when you try some. It says determine whether each graph given below is the graph of an even function, an odd function, or neither, because it doesn't have to be even or odd. It can be actually neither. So this first graph that we have looks something like this. Okay, so let's just pick a point. Let's pick this point. We're going to call that point xy. That means that I went over X number of spaces, over to here, right to here, and then I went down Y number of spaces. All right, so if I go over the same number of X spaces and I go down the same number, is that point on the graph? Yes, it is. So if the point here is XY, then I also have negative XY. You can actually count these. You can see, I didn't draw mine to scale, but you can actually count them on your sketch. So we know that is an even function because it has symmetry to the y-axis. Now, if you understand symmetry, you know that it means that the right-hand side is a reflection of the left-hand side, and you can tell that by looking at it. You can tell by looking. All right, let's look at this second graph. That graph looks something like this, and then it keeps going. Oops, that was supposed to touch right there. All right, pretend that touches. Okay, it keeps going in that direction. And what we want to know is that, does it have symmetry to the y-axis? That would make it odd. To the origin, that would make it, to the y-axis would make it even. To the origin would make it odd, or is it neither? Well, let's draw this line, the line y equals x, right there. All right, is that graph symmetric to that line? If it is, it's symmetric to the origin. Well, another way to think of it, because some of you can tell just by looking and by seeing, is let's find some points. So if I go here, let's talk about this point right here. That's the point xy. Okay, if it is even, I will also have the point negative xy. So if you go over here and you look for the point negative xy, I don't have that point. So it's not even. If it's odd, I will have the point negative x, negative y. Well, that point isn't on the graph either, so it's neither. It's neither even, symmetric to the y, nor odd, symmetric to the origin. It's kind of hard to see if you can't just look at the graph and tell. It's a little bit hard to figure with the xy points. Okay, let's look at the next one, and it looks something like this. Okay, pardon my artwork. All right, and we want to know, what is it symmetric to? Okay, so let's take a point on the graph, a point here, xy. So that point went over x and up y. So if I can go over the same number of x's and down the same number of y's, okay, that would be a negative x and a negative y. And that point's on there, which it is, then it is symmetric to the origin. So this is odd because it has symmetry to the origin. And also because the point xy and negative x, negative y are both on the graph. For any xy that I pick, I can pick any xy. I can pick this one. There's its corresponding point. I can pick this one. There's its corresponding point, etc. of negative x, negative y. So symmetry to the origin makes it odd. All right, let's look at the back. It says identify even and odd functions from their equation. And honestly, because I'm not a visual person, I think this is easier than it is than identifying them from their graphs. Probably most of you are going to disagree, but some of you will be with me on this. So let's look at example 2. Rather than looking at the graph, we're going to look at the equation. So in example 2a, we've got f of x equals x squared minus 5. And we want to know if it's even, odd, or neither. And that will tell us whether it's symmetric with respect to the y-axis, the origin, or neither. Okay? All right, so let's just kind of get organized here. If it is odd, then we know that f of negative x will be equal to f of x. That's for odd. I meant negative f of x. Sorry. Odd. F of negative x will be negative f of x. If it is even, f of negative x will be equal to f of x. And if those two things aren't true, then it's neither. So let's start and let's check to see if it's even. All right, so if it's even, remember, f of negative x will be equal to f of x. So let's find f of negative x. That's what we do to test if it is even. So f of negative x would be take out the x, put in a negative x, keep the rest the same. F of negative x equals negative x squared is just x squared, but x squared minus 5 is the same as f of x. Therefore, f of negative x is equal to f of x, and we now know that this function is even. Okay? Now we can test to see if it's odd, but it's not going to be. So let's just test that and I will show you. If it's odd, then f of x will equal negative f of x. Alright? Excuse me, f of negative x would equal negative f of x. Well, we just figured f of negative x. F of negative x was equal to x squared minus 5. But negative f of x would be the opposite of our original equation, which is negative x squared plus 5. And that is not equal. F of negative x doesn't equal that. So no, it is not odd. It's an even function. Okay, let's go to B. We've got g of x equals x cubed minus 1. Okay, now let's think. We want to test and we want to see what is g of negative x. Because if g of negative x equals g of x, then it is even. And if g of negative x equals negative g of x, then it is odd. So we're going to test. That's the key. G of negative x. So g of negative x equals, take out the x and in parentheses put negative x, cube it, minus 1. G of negative x is equal to a negative raised to an odd power is a negative, minus 1. Is that equal to g of x? No. So it's not even. Is this equal to negative g of x? Well, let's see what that is. Negative g of x would be the negative of x cubed minus 1, which is negative x cubed plus 1 if you distribute that. Are these two things equal? No, so it's not odd. So what is it? It is neither. Neither even nor odd. Each time we're just going to check for the function of negative x. Alright, so let's look at C. We have h of x equals 5x cubed minus x. So what do we want to test? We want to test h of negative x. So h of negative x would be 5, take out the x, put in the negative, cube it, minus, take out the x, put in the negative. You have to do it in each place that there's an x, so here and here. Let's simplify this a bit. A negative x raised to an odd power is negative x cubed times 5 is negative 5x cubed. Negative times negative is plus x. Now let's first check. Are those two things equal? In other words, does h of negative x equal h of x? No. So it's not even. Now let's ask this question. Does h of negative x equal negative h of x? Well, I don't know because we didn't figure negative h of x yet. So let's do that. Negative h of x would be the opposite of the original equation, which is equal to negative 5x cubed plus x. Okay, does that equal that? Yes, it does. So what is it? It is odd. Again, each time we're checking for the function of the negative x. All right, let's look at D. D is tricky. F f of x is equal to absolute value of x. So of course, we are going to test what is f of negative x. So let's just do that. F of negative x, now hang with me, that would be absolute value of that, negative x, but that's the same thing as the absolute value of negative 1 times the absolute value of x. I can split that absolute value into a negative 1, because that's really negative 1x times x, but the absolute value of negative 1 is just 1, and so we have 1 times the absolute value of x, which is just the absolute value of x. Does that equal that? Yes, it does. So the function is even. A little bit of a tricky one. All right, let's look at this little summary section about increasing, decreasing, and constant intervals. Oops, constant, spell it right here. Constant intervals on a function. The first bullet says, always look from left to right as the x values get larger. You look from left to right to see where is it increasing, decreasing, or constant. And then the function is increasing if the y values are getting larger. So if the y values get larger, the function is decreasing if the y values, remember, going left to right, get smaller, and the function is constant if the y values don't change. They stay the same. Okay, so let's look at example 3. It says, find the intervals on which the functions are increasing, decreasing, or constant. In 3a, we have, I'm going to pause to sketch. Okay, that was a tough one to sketch. And I know you see it already drawn, but I just had to pause it and sketch it. So we've got the point negative 12, 6. That's right there. We've got the point negative 9, 0. We've got this point negative 3, negative 5. We've got the point 0, negative 3. We've got the point, it looks like, I don't have anywhere to write it, 2, 0. We've got this point, 7, 6. We've got this point, 9, 0. And we've got this point, 12, negative 6. And the graph actually ends there. Okay, so here's the questions. Where is this function, the graph of this function, where do we see it increasing? All right, so let's just start looking, remember, looking left to right. And you can tell by looking, it is most definitely not increasing here. But where does it start to increase? It starts to increase right here, and it's increasing up to here, isn't it? So how do I show that interval? Where does it start to increase? In other words, what is the x value of where it starts to increase? It starts to increase at negative 3. It doesn't include negative 3, because at negative 3, it's equal to negative 5. It's static there. Where does it continue to increase? All the way up to where x is 7. So I know this looks like the way that we show a point, the point negative 3, 7, but that isn't what this means. This is an interval. And it's showing x, x. It's showing the first x and then the second x of where that interval that it's increasing on. Okay? All right, next. Where is it decreasing? And I'll try to use a little bit different symbol so you can see where it's decreasing. I'll make bigger squirrely things. All right, well, it's decreasing here for sure, isn't it? Down to here, and then it stops decreasing. And then where is it decreasing again? It's decreasing over here. So those two big swirly things is where it's decreasing. Well, what are the x values, the x intervals? It's decreasing from x is negative 12 down to x is negative 3. And then we union that with what is x here? 7 to 12. That's where it is decreasing. Where is it constant? Well, that's pretty easy to see, because if it's constant, it would be flat, and nowhere. Nowhere is this graph constant. Okay, let's look at our next graph, and once again, I will pause to sketch. Here's the points we've got. We've got the point -9, 7. Here, it looks like we have the point -6, 0. We've got the point -4, -5. We've got the point 0, -5. We've got the point 6, -5. This side isn't drawn very well. We've got the point 9, 0. And then we have the point 12, 7. Okay? Same questions. Where is this graph increasing? So when you look, going left to right, it doesn't start increasing until right here. Correct? So what is the x interval over which it is increasing? It starts at 6, it ends at 12. So that's the interval over which it's increasing. Where is it decreasing? Well, we can tell by looking that it's decreasing, I'll make these big, over that interval where x is -9 to x is -4. And the next question is, where is it constant? Where is that graph? Does it have a flat spot? Yes, it does. And I'm going to do that like this. It has a flat spot right there. And what is that interval over which it is constant? It's the x value of -4 all the way over to x equals 6. That's all we're doing. All right, let's look at the next section, which talks about local min and local max. We're going to define these. A local max, that's your first blank, is a point where a function changes from increasing to decreasing. So max goes from a function being increasing to decreasing. Think about it. Increasing to decreasing. That's going to make a max point right there. Here it's increasing, here it's decreasing. So it makes sense when you kind of sketch it. A local min is the point where the function changes from decreasing to increasing. So it's decreasing and then it starts increasing. And what do we have? We have a local min there. So it's going from decreasing to increasing. Easy to figure out, again, if you sketch. The min or max value of a function is the y value located at the x value. And that is a little bit confusing. So let's take a look.